Hi everyone, welcome to Modern Optimization Methods. In this part, we will look at 2.4, the fourth part of Chapter 2, Line Search Strategy. In this part, we will mainly introduce the overview of algorithms and the line search strategy. Now, let's take a brief look at numerical algorithms. As we mentioned in Chapter 1, the numerical algorithms actually starting from initial point x0 and then iterate until it reaches some stopping criterion. So it will generate a sequence xk, and the stopping criterion may setting as follows. If there is no progress, then we will stop the iteration, or if we reach an approximate solution, then we will also stop the iteration. Now, as we mentioned before, the key point is how we move from xk, the current iterate, to the next iterate, xk plus 1. As long as we figure out this process, then we can design numerical algorithms. Now, naturally, there are two ways to generate the next iteration. We will detail in the next slides. Now, the currently information we may use include the current function values fxk, or even more previous function values, including fxk minus 1 until fx0. Also, if the function value it is differentiable, we may also use the gradient information. The main aim in this case is that we try to reach a smaller function value than the current iterate. Okay, so this is our objective. Now, let's take a look at how we move from the current iterate to the next iterate. There are basically two strategies. The first one is the line search strategy. The second one is the trust region strategy. The two strategies have different ideas to design the next iteration. Now, in this part, we first take a look at line search strategy. For line search methods, the main idea for line search methods is like this. We standing at the current iterate, and we choose a direction. For example, we choose the direction here. Then we move along this direction at a step size alpha k. Okay, so then this will be the next iteration. All right, so mathematically speaking, the next iteration will take the following form: xk plus 1 equals xk plus alpha k multiplied by pk. Now, there are several definitions. The pk which we choose is called the direction. Okay, so this is the first step. We choose the direction pk. After we get this pk, then we need to choose a step size alpha k. Basically speaking, the main idea for line search strategy are divided into two steps. The first one is we choose a direction. The second one is we choose a step length. Okay? Now, let's take a further look at the step length. How we determine the step length? In other words, how large I will move along this direction. So, the idea is that we try to minimize a one-dimensional function value phi alpha in order that we can reach a smaller phi alpha. The returned solution is actually the step size. Okay? So we have two ways to find this step length. The first way is that we do exact line search. That means we solve these minimization problems to reach the global minimizer. Then this global minimizer will be the exact line search step. In another way is the inexact line search, which means that the step length may not be necessarily the global minimizer of the problem. However, we just require that the step length achieves adequate sufficient in terms of function value. Alright? So there are different concerns for the two kinds of step size. For the exact line search, the benefit is that we can reach a global minimizer of this phi alpha. In other words, we can get the smallest function decrease along the direction pk. However, to achieve this goal, we need a lot of function values, alright, because we need to find the global minimizer. It may involve a lot of computational cost and a lot of inner iterations. Another way for inexact line search, the decrease in function value is adequate reduction, alright? So there are some adequate reduction in this function value. However, alpha k can achieved by using lower function value cost. Okay? In other words, the inexact line search can save some computational cost. Meanwhile, it can reach some adequate function reduction. Alright? Now, in terms of line search methods, there are different ways to determine the search direction, pk. Okay, so here I list some of the different ways to determine the directions. For example, if the direction is determined by steepest descent direction, then the resulting method is called steepest descent method. Similarly, we can also determine the direction by Newton's direction, or by quasi-Newton directions, or by conjugate gradient directions. So there are different ways to determine the directions. Now, let's first take a look at the steepest descent direction. So from the name, you can see that the steepest descent direction actually reduces the function value in a very fast way. Okay? So let's take a look at what is its form. In this case, direction pk is taken as the minus of the gradient. In other words, it is the negative direction of gradient. Let's recall that for a gradient of a function, it actually represents the fastest way that a function value grows. Okay? So if we take the minus of this gradient, it actually represents the fastest way that a function decreases. Okay? So recall that we are trying to minimize a function. Okay? So we try to find the fastest way that function value decreases. Okay? So this direction actually returns us the steepest direction. Now, we have a simple result, okay, which explains why this direction is called steepest descent direction. So the result basically says that among all the directions, the steepest descent direction actually the one that along which the function values decreases most rapidly. Okay, so this is a result. We put it as a theorem. However, here we did not give the proof. I leave the proof to you as a homework. All right? After giving the steepest descent direction, let's take a look at a graph to show how steepest descent direction works. Now, look at this figure. So we got some curve or some circle here, right? So as we recall that this circle represents the contours of a function. So, suppose we are standing at xk here, and we try to choose a steepest descent direction. So it is actually orthogonal to the tangent line here, all right? So this will be the steepest descent direction, pointing to the minimizer, all right, pointing inside. Okay, so the steepest descent direction actually put this way. And then if we move along pk at some step size alpha k, then we jump to a point xk plus 1. Then in the next iteration, we still choose the steepest descent way, and the iteration goes on. All right? So this actually shows that the steepest descent direction is orthogonal to the contours of f, all right? Because it's pointing directly into the minimizer. Right, so for the steepest descent direction, we have some remarks about this. The first remark is that the advantage of this direction. As you can see that it actually requires only the gradient information, which means that the computational cost is not that expensive, right? So we just need the gradient, all right? And the disadvantage is that it may be extremely slow for some particular examples, all right? Because in some very bad situations, if you move along the steepest descent directions, there will be very slow convergence rate. We will discuss the convergence rate later in chapter 3. And more extensions is that if we choose other directions, not steepest descent directions, so what kind of conditions we can choose? So we give a definition here that any direction pk satisfying the condition here will be a descent direction. So what is this condition? This condition basically means that pk take inner product with gradient of f at xk will be strictly smaller. In this case, the direction pk will be a descent direction. All right? So why in such condition it will be a descent direction? We still use the Taylor's expansion here, and we move along fxk along pk with a very small step size epsilon. Then we can get the second order Taylor's expansion, and we can see that when this epsilon is small enough, then as long as this term pk transpose gradient fk negative, then the function value of f at xk plus epsilon pk will be strictly smaller than fxk. Okay, so this somehow explains the intuition why pk satisfying this condition will be a descent direction. Okay, so after we give the descent direction here, then the next question is that how we can choose other descent direction in order to get a round of slow convergence like steepest descent direction. We will talk about this later in Newton's direction, quasi-Newton's direction, and also conjugate gradient directions. Now, for this part, let's make a brief summary. In this part, we have introduced the line search strategy. Okay, so there are two steps in line search strategy. First is step length, how we determine a step length. The second one is search direction, how we determine the search direction. Here, we only introduce the first search direction, the steepest descent direction. And for other directions, we will talk about more later in the next part. Until then, see you next time.